All right. Thank you all for the opportunity to speak, and thank you to everyone who's made it through the day so far to listen to me speak. So yeah, I'm very happy to be here, and please interrupt me at any time if you have questions. I read the email last night and hastily extended the length of this talk, so if the pacing is funky, it's on me, but it's also hopefully understandable. So yeah, so if I rush through anything, slow me down. All right. So the general theorem that I'd like you to have an idea of by the end of today is that nothing infinity categorical on my end, but that falls out of an infinity categorical result by Walker-Stern from 2019, which is that if we take isomorphism classes of two Siegel simplicial sets, we'll talk about what that is, then there's an equivalence of categories, which I'm only going to talk about at the level of objects, with pseudomonoids, so coherent algebra structures in this bi-category of spans. Extensions of this result recently, because we're interested in topological quantum field theories, we're in commutative convenience algebras for any clear reasons that I can expand on. And then my current work has been most recently with my advisor to extend to the commutative Frobenius case, and now I'm working with double two Siegel sets, figuring out bialgebra and Hopf structures. So won't talk about that today. Happy to talk about it after.
Sorry, can I ask a question?
Yeah, of course.
What's the first? Which Stern is that?
That's Walker-Stern. He's yeah, okay. Yeah, absolutely. Okay, great. So I normally talk to physicists who need a lot more motivation about this sort of thing. For you all, this may be a little more natural. But given a category C, we probably know that we have the nerve construction, which gives us a simplicial set from C. And going the other way, if we have a simplicial set and we want to know if it's the nerve of some category, then we see if it satisfies the Siegel condition. Which we then generalize, because we like categories, to the idea of a Siegel space. Then the generalization that I work with is this two Siegel condition. This was come up with pretty much independently by the first set of authors under the alternate name of the decomposition space, because they were mostly interested in sort of combinatorial examples and coalgebra structures. And then also by Degerhoff and Kronov under this name. And their general motivation was that they were sort of coming out of this like Baez-Dolan categorification program, and they were curious about the different kinds of algebras and coalgebras that we could decategorify from two Siegel spaces. So yeah, so the result that the first result is a corollary of is this result by Walker-Stern, that if you take the infinity category of spans in some infinity category with finite limits, then the two Siegel objects in that category are some version of coherent associative algebra object in your infinity category of spans. I'm just going to talk about sets. So that's a beautiful paper, and you should absolutely go and read it. But he knows much more about infinity categories than I do, so yeah, that I will refer you there for that. So yeah, so basically this is sort of a cool accessibility thing. It gives us license to use a really beautiful graphical calculus to make our arguments. And it sort of brings a lot of the nice categorical information over to, people from other areas of math and physics, and maybe pure topologists who might not have some of the infinity categorical background that all of you do. Many of you do. Yeah. And then in future work, we're working on upgrading all this from sets to groupoids, and also on the sort of like 3D situation. So this is work by Baez, Hoffman, and Walker. There are a bunch of different monoidal functors that go from spans of groupoids down to vect. So essentially, the game is we think of interesting associative algebras that we might like as, potentially QFT related, or maybe we're just curious about algebras and we're looking for the structure that decategorifies to this thing. So if you're looking at a simplicial set, you can just take the vector space spanned by x1, and so this is inducing linear maps, vector spaces, and we use this sort of push-pull construction where as long as that map F has finite preimages, we can sort of take this as like a direction ambivalent morphism in linear algebra, I guess, and go from X to Y via these linear maps, which give us algebra structures. All right, so yeah, one of the key examples that we look at in our work is this idea of Hall algebras, which is probably the most straightforward way to decategorify. So you take a two-Siegel set with a finite X naught, and such that that pair of face maps has finite pre-images because that's sort of what's showing up in the left leg of your span. And then you take the Hall algebra, you take the vector space formed by your one simplices, and multiplication is given by this sort of form of sum here, the image of your face map D1, and the identity element is given by the image of your degeneracy maps. Yeah, so everything here is sort of like nice and automatic because we're just working with sets and we can pull back and push. All right, so how I'm going to look at this category span, which I'm going to henceforth just write span, I'm writing span set. Is as a monoidal bicategory, so please don't expect any on the nose associativity ever from me. So I will rephrase the problem as sort of wanting to understand monoid objects in fact, so what we think of as associative algebras as decategorifications of these things that I'm calling pseudomonoids in the bicategory span set, which is kind of the natural categorification of this idea. We have an algebra which has an associator, but this associator is in interesting cases non-trivial. Some two-morphism. Okay, so cool. So we've got a bicategory of spans. Our objects are just sets. Our one morphisms are spans of sets, as we saw. Yes.
It's a monoidal bicategory.
It's in fact a symmetric monoidal bicategory.
Those things like very complicated symmetric monoidal bicategory.
Yes.
The coherence diagrams still like.
Yeah, I've elided them because they suck. But I will say a little more about that, and I will in fact say more about that in string diagrams. So hopefully you can sort of like see the rules of the game that we're playing without being exposed to trauma. But yeah, they're a little bit awful. But the moral of the story is because we have, you know, pullbacks being sort of literal fiber products and everything, and we have a lot of very nice theorems that tell us everything works out. We don't have to deal with the horror of what you're envisioning. Yeah, it's a really good question though. So yeah, so we've got sets and spans of sets, and as we heard yesterday, pullback is our one morphism composition. Different from yesterday, our monoidal structure is just going to be Cartesian product of sets. So no disjoint union here. We've got an identity span. Yeah, and two morphisms are sort of those really just on a set maps H, such that that diagram completes. All right, so yeah, so this is maybe what you were alluding to. So we've got a lot of further data to guarantee cohesion in a monoidal bicategory. But the associator just comes from the universal property of pullbacks because we're only working with sets. Same for the uniters. And then this sort of further information, so this isn't really higher data, this is just how I draw the monoidal product in string diagrams in case someone hasn't happened to see it before. All of this can really be written most nicely using string diagrams, in my opinion. So my double arrows are all just two morphisms, and then this is sort of how we can express that higher coherence and braiding data from the bicategory. Happy to point you to the awful commutative diagrams if you prefer that approach.
What does that last word say?
Solipsis.
Did I ask what that means?
I don't know what it literally means. Like Greek
No.
wise, I don't know what it actually means. What it really is here is it's expressing the symmetry of the braiding, but it's not doing anything more interesting than that. Yes.
It's an exagenator.
Yeah. Okay, so it has something to do with the compatibility of the associator with other two morphisms. So that the coherence like diagram for that, the commutative diagram looks like a big hexagon, and it's the thing that makes the big hexagon commute, hence hexagonator. So yeah. Yes. Okay, so let's say what I mean by a pseudomonoid. So again, this is just my sort of bicategory level algebra object. So I have an object in my bicategory. I've got a unit morphism and a multiplication morphism, some binary morphism there. And then I've got these invertible two morphisms, the associator and the left and right uniters. So just a categorification of the idea in algebra. This only has to satisfy two covariance conditions, so this is less awful to write down. The triangle equation basically is compatibility of the uniters, and the pentagon equation takes care of associativity. Again, because I don't want you to have to look at massive commutative diagrams, we're going to express everything via string diagrams in a way that I hope I'll make rigorous. So here's the uniter. A hollow circle just means it's a nullary operation, so I'm going from nothing to something. And after this slide, I'm going to take out the object labels because we're only working with one central object, the x1 in our simplicial set, so hopefully the sort of object we're working with is implied. And then these double arrows are giving my two morphisms and maps. So this is how we can then represent our coherence conditions. So what the triangle equation is doing, if you're not used to looking at these, is it's just this sort of like topological shrinking of the nullary operation into the binary operation from both directions. And then the pentagon equation. The dotted boxes are sort of where you apply the morphism. So that's sort of how to read a string diagram like that. Yes.
We should know this because I'm talking about this tomorrow. But I count 6 things, right? Like down here.
Yeah, two of them are the same thing. So if I had written this nicely as a pentagon, it would sort of close up, but because I've unwrapped it into like a linear diagram, I think you're seeing one extra.
I guess I meant like
Oh.
I see 6 arrows, right? Like
Great. Okay, that's fair. This guy becomes trivial, I think, for our purposes. So I think that's gonna.
oh, I see, because there's a little shift.
5 sides.
Yeah. Okay, so there's a shift, yeah.
So if I was thinking about a hexagon, then you wouldn't have a question, but yeah, that makes absolute sense. Yep. All right, so what I'd like you to have some idea of is the idea that we can take a two-Siegel simplicial set and produce a pseudomonoid from it, and then I'll give you some idea that we can go back the other way. All right, so we've probably all seen the definition of a simplicial set many times. This is just to sort of fix the notation that I'm going to use. It's this contravariant functor from delta off to set, and it is coming from the sort of generating maps in that category. So we'll see our sets, xn, our base maps, which I called BNI, and I will sometimes take away the upper indices when clear. Degeneracy maps SNI, and they satisfy the well-known at this point relation. So the sort of perspective that I care about is, the Siegel condition says that whatever we're working with is in some sense category-like in that we have a composition, it's defined, it's unique, it's associative. In so many words, it's saying that we have an isomorphism from any n simplex to these fiber products that are really fiber products over X naught. So what I'm worried about is the two Siegel condition, which is the sort of level up generalization of this idea. So the one Siegel condition ensures things are strictly associative. The two Siegel condition ensures that we have an associator, which is an isomorphism, but which is in interesting cases non-trivial. So now we have an isomorphism called the two Siegel map that goes from any n simplex to now x2's fibered over x1. So triangles fibered over edges, essentially. This means that two Siegel sets have a really beautiful presentation just as planar n+1 gons with subdivisions. So the most basic way is to see this map, which we call the spine map, and think about it as triangulating your n+1 gon. So xn is a regular n+1 gon, and when you take it and break it into x2s, then you triangulate. And the fact that this is an isomorphism means that we can sort of look more generally at any subdivision because the associator says that anything would be a sort of triangulation area. All right, so this means that we can also make a shift on this side of the correspondence into a graphical calculus. So here, say I've got an element of X3, or sorry, X3. And all I need to do to apply a face map is to sort of say, I'm deleting the simplexal level down at vertex I. And then same with the degeneracy maps. You're inserting a degenerate one simplex that opens up sort of a degenerate edge, which I'm calling a dotted edge, from vertex I to I+1. All right, so then this is sort of how the simplicial relations look under this graphical calculus, just to give an idea of where you can sort of see that there's like lossy information or information. All right, so the first example that we can see of a two Siegel set that's not also one Siegel is if we take the nerve of a partial monoid. So this is a monoid, but instead of the multiplication being defined everywhere, we just pick a distinguished set of elements where it is defined, and we say this is associative when it's defined, and otherwise it doesn't exist. I mean, your scientists and symbolic logic people kind of like. So we take the nerve, very similarly to the nerve of a category. We just got a single object, so and not is just one thing. And then we take morphisms, and morphisms such that all of the sort of n-1 tuples are composable at each level, such that they're in the sort of approved multiplication set. And the face and degeneracy data is just the same as for the nerve of a category. So to get even more concrete, here's the simplest partial monoid I can think of that does anything. So you can see the multiplication, and then maybe just more concretely how the 1 simplices, 2 and 3 simplices look. This will become relevant later. Another example of what I mean, because I like coordisms, so the nerve of a partial category. So same idea as a partial monoid, but we've got more than one object. So here the rules are, we take essentially, so this can complete to just the nerve of a category, but for now, we cap the genus of our cobordisms, and we take, so the objects of our cobordism category here are just disjoint unions of circles. The morphisms are, cobordisms from circles. And then the rule is that you not only have to have each piece be genus restricted, but your composition is similarly genus restricted. All right. So to make clear graphically what I mean by associativity, so we'll look at these simplices with the sort of first non-trivial case of triangulation, like triangulate one of two directions. And note that these T-maps are isomorphisms because that is what it means to be two Siegel. So this is going to be the associator for the pseudomonoid that we want to build. All right. So to see why this works, we rely on sort of dualizing these shapes as graphs. And well, you can sort of see how an associator pops out. We've got one parenthesization on one side and one on the other, and then this sort of triangulation ambivalent shape connecting the middle, which we can associate with our untriangulated square. How do I make spans out of this? Well, I sort of read top to bottom, right? So a string diagram goes input objects to output objects. Similarly, I can see this as a span from the top stuff to the bottom stuff, where the sort of ambient space in the middle is where the operation is happening. So this here is a span from x1 cubed to x1. And in general, we'll take the span that goes from n copies of x1 and no question, and assign it to any n plus 1 valent vertex. So if we take a trivalent vertex and assign it to this span, then we have the multiplication. So if we take our edge set as an object in my category by category of spans of sets, then I can take this map of string diagrams and write it in terms of my two Siegel isomorphisms. It looks worse as spans, but also works. And so the idea is that this gives us an associator which satisfies the pentagon identity, so the coherence conditions that I'd expect of an associator. And this is what the proof looks like. I mean, okay, this is my graphic of what the proof looks like. So I sort of I take face maps to get to something 1 degree down, and then I've got my 3 simplices, and you can sort of see that each one of these triangles commutes and the gluing of all of them.
Can you remind us what we are trying to prove now?
Ah, sorry, yeah, that's totally fair. So the pentagon identity, let's pop back to it. The bottom of this slide. So we just really want to say that if you associate and reflect in all of the possible ways that that diagram commutes. So really what's going on is that sort of each corner of this diagram is one string diagram from the pentagon identity as shown before. The intermediary steps are these untriangulated versions, and the Q-sequel isomorphisms allow us to sort of traverse from vertex to vertex. Yeah. All right, so what else do we need to make a pseudomonoid? We need uniters. So here we kind of just go with the sets that we think should work. So you can construct this span as a pullback. This is just what it means to be a uniter. You need something. Yeah. And so this is just for the left associator. So in order to understand what isomorphism it is, flip the identity span and understand what both sides look like. So in this case, we take the pair U psi from a pullback, and one direction of this map is just coming from the face maps and the simplicial structure. The other direction comes from the fact, which wasn't actually discovered in the first few papers about two-Siegel spaces, that unitality automatically holds for all two-Siegel spaces. So this was a result of Feller's one, that all these sorts of squares are all Cartesian. We also have higher unitality conditions that are automatically satisfied. These are sort of like 3 co-skeletal things, so you can care about things up to. And then the last thing that we need to say is that our uniters satisfy the triangle equation. So here's what eta looks like, right? It's going from a point to x1, our monodal unit. And then how it looks as a string diagram. And then again, similarly to how I drew it for the pentagon equation, this is sort of what we expect from the triangle equation. And the proof comes from noticing that this sort of guy with 2 arms sticking up is a valid isomorphism to our multiplication span. But come on, you can't unsee it now by our unitality conditions. This is true, right, for multivalent vertices by higher unitality as well. So you construct this isomorphism S, and then you can write out your associator and your left and right uniters all in terms of these maps that everything commutes.
But why did he fall over?
He fell over because I was really tired last night and freaked out that I hadn't put this diagram in, so I put it in again and it didn't fit, so I put it at an angle. He fell over because I was jet lagged, is what happened.
It makes sense.
All right, so yeah, so all in all, this is sort of the data packaged together nicely as string diagrams to say that the two-Siegel condition is sufficient to ensure that we get a pseudomonoid object in span. Questions at this point? Going the other way is sort of a similar idea. There's a coherence theorem for pseudomonoids that is, as far as I can tell now, cited by everyone as sort of like a folk theorem. If anyone has the first resource for this, please let me know, because every time I ask someone, they say someone else. But that ensures the sort of whatever choice we make in rearranging string diagrams, as long as we have an isomorphism, we sort of found all of them. So we create n-fold products and kind of step backwards through essentially a similar argument to what I gave, dualizing to get the other way. So the interesting extensions of this idea are that, so if you're interested in QFT, you maybe know that 1 + 1 dimensional topological quantum field theories are the same as commutative Frobenius algebras. So that's sort of the motivation for these extensions. So there's a theorem by Contreras Stern that the Frobenius pseudomonoids are these paracyclic sets. So going from the category lambda infinity, the commutative ones go from V star, which is just the skeleton of Finn set that fixes 0 every time. And the commutative Frobenius ones are in fact what you'd expect them to be, which we were worried it wouldn't be, that you can just take category finite sets and take an actual commutative plus Frobenius. So yeah, just to say a little bit about what I mean by that. A cosymmetric set is a simplicial set where we have just an n+1 action, so an extra set of permutation maps that satisfy these compatibility conditions. Yeah. And because they're permutations, we also get to use the Moore relations to manipulate them. So you can also think about this if you've seen the cut functor, which also is relevant in the definition of paracyclic set. You're just sort of adding permutations into the output of the cut functor, which takes interstices between the sort of elements of a set to go from delta off to this version of this.
Could you
Yeah.
unwind what a cosymmetric set is as a functor out of something? What is it something?
So it's just going from this skeleton of Finn set to set. So delta op embeds in Finn set if you sort of allow permutation, because delta op is just taking the like weakly order preserving maps, and so you can undo that restriction by permuting. Yeah, okay, those slides were in the wrong order. So this is what I actually wanted to talk about next, which is the paracyclic idea. So we want to say that paracyclic simplicial sets are Frobenius pseudomonoids. So, chalk. Is this more visible or is that more visible? This is more visible. Okay, so maybe you've seen or maybe you haven't, but the Frobenius condition is this sort of snake lemma that we can unwind to an identity and the other way. And here there's a pairing and a co-pairing, and we want that this guy is bi-exact or non-degenerate, depending on what language you use. So algebraically, that's what we're looking for. And then the functor we're using is coming from lambda infinity, which it embeds nicely into the cyclic category, which is maybe a more familiar category. This condition on morphisms meant almost nothing to me when I started, but it's a sort of spiraling condition that you have something that's like almost cyclic. So yeah, so we have a functor from lambda infinity off to set. And we can express it in a way more familiar in terms of just looking at simplicial sets by saying that we have isomorphisms tau which induce extra degeneracy maps. So basically in every degree, you have one extra degeneracy map given by a sort of rotation and application. Okay, so we can use this idea to construct the appropriate co-unit. This again also uses the same unitality square, which is due to Feller. And we take a version of, so this is not the same co-unit you'd use if you would want to construct a bialgebra, because it won't work out as compatible between an algebra and coalgebra structure despite the symmetry. But instead you use the one that involves the extra degeneracy map, and this is enough to give you a Frobenius co-unit. Yeah, so essentially you're just working composites of spans and checking isomorphisms. Yeah, so your extra degeneracy map is inducing a Frobenius structure. So it turns out that the partial monoid, the very simple one that we looked at at the beginning, was in fact a paracyclic set. It's more than that. It's in fact just a cyclic set, which would be a symmetric Frobenius algebra, which is maybe more than we usually want, but just for the purposes of illustration. So your tau performed on the right side is taking element A to element B. And you can sort of see maybe more clearly how the tau isomorphisms are expressed in terms of the extra degeneracy map in the graph. Another one, so we can take the twisted cyclic nerve of a category, or of a group if you want. So again, very similar to the nerve of a category, but we also equip our category with some endofunctor. And we add an extra condition that we can sort of wrap around using the image of this endofunctor.
Yeah. Where does this sort of does this come up in nature somewhere? Like, are there examples where having like can you give an example of a twisted or of a category with an endofunctor where the twisted nerve is something that I would like?
So I've only seen this reference where they're like, and also it's trivial. So I don't know if there are interesting examples that come up. Yeah, unfortunately I don't know.
No worries, no worries.
Yeah, totally fair question though. So again, this is what it looks like. This is kind of the like oriented necklaces perspective. Also, you can maybe see the rotations going on. And then I flew through that. All right, so yeah, so what we've been up to, we recently rewrote a review paper that gives sort of both directions of the correspondence. And then I'm using double two Siegel sets with various different conditions to play with bialgebra and Hopf-like structures. And we're also curious about sort of Hopf categories and going into the 3D QFTs. And these are the things I used. Thank you very much.